Hi there, I'm Clément. In my last video, we had a look at how the processor and the compiler is going to handle the fact of going over the bus size when you're doing some calculation. For instance, in my case, I'm using a 32-bit microcontroller. What happens when we do a 64-bit addition, for example? Turns out that the results were disappointing. It's doing a little bit more calculation, but just a tiny little bit more. And I'd like to see a little bit more destruction. So we're gonna have a look at something that I'm for sure know is gonna create a lot more code. The reason why I know that it's gonna create a lot more code is that because it's one of my most trustworthy, most reliable trick for saving space in a microcontroller. In every project, you're gonna have to save space at some point or another because that new feature that you want to implement does not fit. And one of the best tricks to implement in that case is to actually remove all the floating point calculations. That would work only in a microcontroller that does not have an FPU. An FPU is gonna be a processor with some specific instruction that is able to do calculation on floating point numbers. Cheaper microcontrollers are not gonna embed such a device because that saves costs. But more advanced microcontrollers are going to have an FPU and are going to be able to do an addition between numbers with commas in them as easily as regular integer numbers. The precise microcontroller that I'm using actually do have an FPU, which allows us to use it or not if we want, and that way we can see the compiled code and the differences between the two generated X files. Let's see that. So here I have my main function that is extremely simple, just two floating point numbers that are added into a third one that is also a float. If we compile it and we go into the object that is created, we're gonna see that it's actually a very simple piece of code. We just got some two weird stuff that look like loads, some addition and a store, what seems to be like a store, and then we loop back out. So that looks very similar to the addition that we saw in the last video for integer additions. Let's save that. We're gonna also save the size of the X file that is generated. We got 10,847 bytes for the X file that is generated in that precise firmware. It's not very important about that specific number in absolute. The question is mostly what is going to be the difference when we disable the FPU. Let's do that right now. We go in the makefile, and in the makefile we're going to have some commands that tells to use the mfloat ABI hard, so the hardware implementation of the floats. We're going to comment those to force it to use some software implementation of it. What could go wrong? Another way. Oh, there we got some ABI hard. Nope. For float, everything is actually. So we didn't change anything to the main function or to any C software, but if we have a look a little bit more at what happens in the assembly code, we're going to have something that looks like that from the L2 loop to the jump to the branch that is from the L2 loop. And we can see that we got a load, what looks like a call to a function somewhere else in the software. And then we come back, we got a move and a store. So apart from that call, everything looks hunky-dory. That's where the sneaky part is. That's where a lot of memory can be saved. That call of a function, well, it's a new function that is going to be implemented. And it turns out that that function is actually extremely big. Every time you use a new function like that, it's going to require its implementation inside of your software. So if you only have floating point additions in your software, it's okay. As soon as you add, for example, one subtraction, there you're going to need the addition, but also the subtraction. Subtraction, yes, that's the word, subtraction. As soon as you add one subtraction in your software, you're going to need to implement it, and you're going to need to, the compiler at least, is going to implement it for you nicely in your software. Now, in that precise case, we only got the addition. So that's just one operation. You can use that as many times as you want. It's implemented now, so it's free to use 10 times, 20 times, whatever. Free in memory, not in processing. And let's see how big the X5 that is generated is in that new case. So if we look at the difference between those two X5s and their size, we got the first one that is using the hardware FPU inside of our microcontroller. It's only 10,847 bytes. If we look at the one without the hardware FPU and for the implementation in software, just of the addition in our case, we got 12,144 bytes, which is 1,297 bytes that are used, but do we really need them or not? That's for you to decide in your own software and finding ways of going around it, or implementing fixed point calculation, which is an entire technique that we might do a video about in the future. But that's it. That's one of the reasons, that is the reason why floating point calculations are to avoid. Regarding memory, it's also a good there are reasons to avoid it regarding precision and errors of calculation in some cases. That's why in embedded system, fixed point calculation are often preferred. Until now that we got hardware FPUs in some advanced microcontroller, it might start to be a little bit more usable in some applications. That's it. I hope that made the use of floating point numbers in microcontrollers a bit more clear, and why some people avoid them, and actually give you the trick of maybe avoiding using it or removing them to save memory if it's something that you need to do in your project. Still, I have to learn how to say subtraction.